Module 4, Lesson 27, One-Step Equations, Multiplication and Division. I can use substitution to determine whether a given value makes an equation true, so we will be using substitution to check our work. I can write and solve equations and inequalities involving real-world problems. Today we are just going to focus on solving the equations. We won't have too much of the real-world problems involved today. I can solve one-step multiplication and division equations by relating an equation to a diagram. We will be using tape diagrams to show the process. I can use substitution to determine if my solution makes the equation true. So I will find a solution, substitute it back in, and make sure that I'm in the right spot. Example number 1. Solving 3z equals 9 using tape diagrams and algebraically. Then check your answer. First, draw two tape diagrams, one to represent each side of the equation. So I have here one tape diagram that is going to be 3z and the other one that is going to be 9. Now the identity that I'm looking for is the identity of z. So I'm going to go back to those first 4 lessons in this module where we learned about identities and think to myself, I've got, and I'm going to use the commutative property, I've got z that I will multiply times 3. That's the same as 3z. But I want to know what the z is. So I've got z multiplied by 3, and then I will divide by 3, and that will give me z. So what I've got in this first box is I have 3 of z, but I would just like to know 1 of z. So I have to split this into 3 pieces so that each one of these is equal to z. Now because we have an equal sign, I know that my 3 z's are equal to 9. My second tape is equal to 9. My first tape was equal to 3 z's. Now my first tape got split into 3 pieces. Because these two expressions are equivalent, I now need to think to myself, what would happen to the 9 if I split it into 3 groups? How big would each group be? What would the value of each of the groups be? Well, 9 divided by 3 is 3. And this is how we would show it algebraically. Here is my identity property that I did up here at the top to get me to z. And here is where I took the 9 and divided it by 3 to find the value of each one of those units. Now looking at these tape diagrams here, I should be able to recognize that z is equal to 3. And I can check that by substituting. Give myself a little bit of room to work here. 3z equals 9. I'll substitute in the value of 3 for the z. 3 times 3 should equal 9. 3 times 3 is 9. 9 is equal to 9. So now I have substituted and checked. So a little explanation. How does this get us to the value of 3? The left side of the equation will equal z because we know the identity property. So we had the 3 times z divided by 3 left me with the z. And I showed you that on the last slide. So I can use the identity property on the left side. The right side of the equation will be 3 because 9 divided by 3 is 3. And I drew the tape diagrams showing if the top one was in 3 pieces, the bottom one can be in 3 pieces. And therefore, the z is equal to 3. And we can check our answer by substituting. I can actually insert the 3 where the z was, and 3 times 3 is equal to 9. So our number sentence is true, our value of z is correct, we're going to do okay on this. So here we have y divided by 4 equals 2. And we are going to use tape diagrams and algebraically, and then we're going to check our answer. So the first thing we need to do is draw 2 tape diagrams. Each tape diagram is going to represent each side of the equation. So I have a tape for y divided by 4, and I have a tape for 2. Now this one is really, it's kind of geeky, but I like this problem. This is a fun one. So the first tape diagram shows us the size of y divided by 4. We need to modify this to show us y. I don't want a fourth of y, which is what this is. I want the whole thing. So thinking about our identity properties, if I have y divided by 4 and I want to get back to y, then I need to multiply times 4. So I need to take and add more boxes onto my tape diagram. I'm going to need 4 sections. Each one of these is 1/4 or y divided by 4. So I need some more sections there. Now, as we're looking at this, we should be thinking to ourselves, well, each one of these is worth 2 because it tells us y divided by 4 is 2. So if I multiplied this times 4, I need to multiply this times 4. I need to add some more sections on here, or multiply to get my full number of sections. So now I can look and say that if all of this together is y, then all of this is equal to y. So y equals 8. So the tape diagram to represent y should be 4 sections. And I'm going to do it again because I want you to see here. So I had y divided by 4, which was one of these little sections here. But y is 4 of these because it was split into 4 parts, so I need 4 of them to make a whole. And each one of those y divided by 4s is 2. Now how do I know that? Because in the original problem it said y divided by 4 is 2. So each one of these is 2. So if all 4 sections together are y, then all 4 sections together are equal to y. So each y divided by 4 section represents a value of 2, and we know this from the original tape diagram, we know this from the problem. So right here in this tape diagram, we can see that y is going to be equal to 8. We've got 4 equal sections of 2, y has a value of 8. Now, how do we show this algebraically? Well, we had y divided by 4, and we multiplied by 4. And that left us with y. And that was where we had one little box that was y divided by 4, and then we increased that to have 4 boxes so that we could have all of y. This was equal to 2. Well, I got to be careful there. Y divided by 4 times 4 is y. The original problem is y divided by 4 is 2. So we were told that one of these sections was 2. So I'm going to have to scale that up so that I can have 4 sections. So that's equal to 2, but I'm going to have 4 sections. So y is equal to 8. So right here, I can show it algebraically. Now, there are lots and lots of different ways that you could show this algebraically. I could do it this way, and that would show what's happening. And I know some mathematicians don't like to see it this way, but I will sometimes write it out this way so that I have that vertical spot for multiplication. And I know that these two things right here are going to negate each other, just like if I wrote them out this way. And I've just got the y. All right. All right, how do we check our answer? Well, we decided that y was equal to 8. So we had the original problem, y divided by 4 equals 2. I'm going to substitute an 8. I decided that y is equal to 8. I'm actually going to stick the 8 in the problem here. 8 divided by 4 equals 2. Now I need to actually do the 8 divided by 4. 8 divided by 4 is 2. 2 is equal to 2. Check. So we check our answer by substitution. We actually take what we decided the variable was worth, we put it back in the problem, and we follow the order of operations. Okay, in class, we have 5 sets, and this would be an exploratory activity. You would work with a neighbor or a group of kids, and you would do one set of 2 problems using tape diagrams, and then we would share and we would talk with each other about them. So I'm not going to go through all 5 of these sets, but I'm going to look at set 1 and talk about how the tape diagrams worked, how the problems were solved. If you want to compare, pause the video and do set 1 before you watch me so that you can try these out and compare your work and your thinking with what I share. All right, here we go, looking at set 1. So the first part of set 1 is we have 2a is equal to 16. So we have a tape diagram that is equal to 16, and we have a tape diagram that is equal to 2 a's, and each one of those a's has the same value. So we can see that the 16 is going to be divided in 2, and each of those pieces is equal to 8. And we can see that a is equal to 8. So here it is with tape diagrams. Algebraically, we had 2a is equal to 16, and we said this was 2 times a, so we divided by 2 to get a, and we can see that the 16 was divided by 2, and it was worth 8. And then we can do a substitution check. We can have the 2 multiplied by the 8 that we found over here. 2 times 8 is 16. 16 is equal to 16. So we have a true number sentence. 8 is the correct solution. So there's the first part of set 1. Second part of set 1. We have b divided by 3 equals 4. So we have 2 tapes of equal size. They're equal because it tells us that they are equal. Here's the b divided by 3, here's the 4. Now if I actually want to find the full value of b, I'm going to need 3 of these sections. This is 1/3 of it because it was divided by 3. So I've got now 3 total sections, and 3 of them together are going to equal b. Each one of these b divided by 3's is equal to 4, and I will have 3 of them because I want to find the total value of b. So I've got 3 groups of 4. b is equal to 12. Algebraically, I've got the b divided by 3, and I multiply it times 3, and that gives me b. The 4 is 1/3 of b. This b divided by 3. 4 times 3 gives me the 12. And then I can substitute. I decided that b was 12, so I'll substitute in a 12 where the b was. Follow the order of operations. 12 divided by 3 is 4. 4 is equal to 4. So the number sentence is true when b equals 12. I know I said I was only going to do one set. I'll do set 2, and then we'll move ahead. although I really like these and think they're really cool. Hopefully you're doing okay. All right, so I had 4 times C is 24, so 4 of C. So there's 4 C's there, and 4 of C is 24. So these two tapes are the same size because my equation says that these things are equal. Now when I look at the 24, I can see that it will be divided into 4 parts. The tape diagram shows that to me. 24 divided by 4 gives me 6 in each unit. And so C, one single C, is equal to 6. So algebraically, I've got 4 times C is 24, and I would use my identity property. I want to reveal the identity of C. So if I multiplied times 4, I need to divide by 4, and that'll give me C. And as we saw with the tape diagram, if I'm going to divide this by 4, I get to divide this by 4, which leaves me with 6. C is equal to 6, and then we've got substitution to check our answer. For the substitution, I take 4, I substitute in the 6, and now I actually follow order of operations. 4 times 6 is 24, which is equal to 24. Everything checks out there. All right, so I have D divided by 7. I have a number that if I divide it into 7 pieces, it's equal to 1. So I've got 1/7 of D because it was divided by 7, and I say it's equal to 1. But I don't want to know 1/7 of D, I want to know the whole thing. So I'm going to have to multiply this by 7. So there are 7 of these. 1, 2, 3, 4, 5, 6, 7. And all together, they are going to make D. Well, if one of these is worth 1, and I now have 7 of them, I need 7 ones, which is equal to 7. D equals 7. Algebraically down here, we've got the D divided by 7 is equal to the 1. Because I divided by 7, I then need to multiply by 7. We're back to our identity property. D divided by 7 times 7 leaves me with D. As we saw in the tape diagram, if I multiplied the D divided by 7 times 7, the 1 is also going to be multiplied by 7. And we have D equals 7. Substitution. D divided by 7 equals 1. I'll substitute in the 7. 7 divided by 7 equals 1. 7 divided by 7 is 1. Is 1 equal to 1? Oops. Yes, it is. And there's my check mark that ran into my 1. All right, so I'm going to move through these other sets. I'm going to pause long enough that if you wanted to try them by looking at the examples, you could. But here we go, some exercises. So we're going to use tape diagrams to solve the following problem. 3m equals 21. So I've got 3 of m, so I'm going to draw 3 of m, because that's what this means, 3 of m. Each one of these is an m. And altogether, they're equal to 21. Now looking at my tape diagrams, I can see that the 21 has been divided into 3 parts. 21 divided by 3 gives me 7 in each one of the units. So each m is equal to 7. So I check my answer now by substituting. 3 times m equals 21. 3 times 7 equals 21. 3 times 7 is 21. Is 21 equal to 21? It is. Now we've looked at enough of these that I'm going to show you a slightly different way to do the tape diagrams. So I've got 3 of m. So I've got my 3 here, m, m, and m. And I know that altogether that's equal to 21. So instead of drawing 2 tape diagrams, I can start to combine my tape diagrams. You could also draw it like this. I like drawing it with the 21 a little bit down because then I can work inside of the 21. I can look and say, oh, my 21 has been divided by 3, so then I have my 7s right there. And I can very clearly see that m and 7 go together. All right, I've got a number divided by 5 that will be equal to 15, or 15 is equal to a number divided by 5. So I've got a 15, and that is equal to a number divided by 5. But I would really like to have the whole number. So I'm going to have to make 5 copies of this so that I can have the whole number. 2, 3, 4, 5. Redraw my bracket here. So I've got each of these is my number divided by 5. And so I'm going to have 5 15s. And 15 times 5, my number is going to be equal to 75. So I did it with the tape diagram so that you could see again how that works, but the instructions say that we are going to do this algebraically. So I've got 15 is equal to a number divided by 5. I don't want a number divided by 5, I want the whole number. So I'll use my identity property, number divided by 5 times 5. And as I saw with my tape diagram, I then need to multiply the 15 times the 5. So these are going to cancel each other out because they're operations that cancel each other. And so I've got my number, and 15 times 5 is 75. So now I've solved this problem 2 different ways. Tape diagrams and algebraically, I have the same answer. Now what I need to do is actually check this. So 15 is equal to 75 divided by 5. Now I need to actually do 75 divided by 5. Excellent. And I find out that 15 is equal to 15. Now, one of the things that I run into with students is they don't actually do their check. Your check with your substitution is really useful. You substitute back in to see and make sure that you're doing the right things. If I were to do 75 divided by 5 and get 12, I should look and say something's not right here. 15 does not equal 12. Now, in the list of things that could be wrong here, it's possible I divided incorrectly. But it's also possible that 75 is not the right number. So the first thing I would do is check my division. And in this case, we would find the division is incorrect. But it is entirely possible that maybe I have the wrong number here, and I need to check that. So don't be afraid to actually look at your check and say, something's not right here. I might need to rethink this. All right, exercise number 3, calculate the solution of the equation using the method of your choice. Well, I'm going to do tape diagram and algebraically. So let's see here. I've got 4 of p. So there we go. So each one of these is p. And I know that that is equal to 36. And looking at my tapes, I can see that my 36 will need to be divided by 4. 36 divided by 4 is going to give me a 9 in each one of these. And if these are 9, then these are 9. P equals 9. Algebraically, 4 multiplied by p divided by 4 is going to leave me with p. The 36 will also need to be divided by 4, as we saw over with the tape diagram. And 36 divided by 4 is 9. So now I have the same solution found 2 different ways. One, tape diagrams, the other algebraically. Now I can substitute and check. 4 times p equals 36. Substitute in the 9. 4 times 9 is 36. Does 36 equal 36? Yes, it does. Exercise 4. Examine the tape diagram below and write an equation it represents. Then calculate the solution to the equation using the method of your choice. Well, two tapes, and they are equal to each other, so I'm going to put the first tape here as 70. My other tape is made up of Q's, and it says there's 1, 2, 3, 4, 5, 6, 7 of them. 7Q equals 70. I could solve this algebraically now. 70 is equal to 7 times Q divided by 7. And of course this would also need to be divided by 7. So 10 is equal to Q. Tape diagram, I could extend my cuts up here and say I've got 70 divided by 7, and each one of these is going to be worth 10. And I can see that Q is equal to 10. And then I need to use some substitution to check. So 70 is equal to 7Q. 70 is equal to 7 times 10. 70 is equal to 70. Check. All right, looking at exercise 5. Write a multiplication equation that has a solution of 12. Use tape diagrams to prove that your equation has a solution of 12. Well, let's see here. What if I did 2 times a number is equal to 24? And I am supposed to use tape diagrams to prove this. So I've got 2 of a number. That's my 2 in there, so each of these is an n. And they are equal to a 24. And I can see that my 24 has been divided into 2 parts. So each of them would be 12. So n is equal to 12. And I could check. 2 times n equals 24. 2 times 12. 2 times 12 is 24. 24 is equal to 24. Check. Write a division equation that has a solution of 12. I did a multiplication. Okay, now I need a division equation that has a solution of 12. Prove that your equation has a solution of 12 using algebraic methods. So what about a number divided by 2 equals 6? Now if you're struggling coming up with, well, what could I write? Just write a fact family that has a 12 in it. It's a division problem. 12 divided by 2 equals 6. 12 divided by 4 equals 3. 12 divided by 3 equals 4. And we're just going to replace this 12 with a variable. No big deal. So I've got a number divided by 2 is equal to 6. And I am supposed to solve this algebraically. So I've got a number divided by 2, and then I'll multiply by 2 using my identities, is equal to 6 multiplied by 2, as we've proved with the tape diagrams over and over again. So I've got a number will be equal to 12. Now I need to substitute. Number divided by 2 is equal to 6. 12 divided by 2 equals 6. 12 divided by 2 is 6. 6 is equal to 6. Everything checks out beautifully. Alright, so how is solving addition and subtraction equations similar to and different from solving multiplication and division equations? Think about that for a moment. Solving addition and subtraction equations is similar to solving multiplication and division equations because identities are used for all of these equations. Boy, we are living and using those identities from those first 4 lessons in this module. Solving addition and subtraction equations is different from solving multiplication and division equations because they require different identities. We are using different identities. It's not A plus B minus B. No, we're doing things like A multiplied by B divided by B. So we're using identities, but we are using different identities, which is why we had 4 different lessons about these identities. So what do you know about the pattern and the operations you used to solve the equations today? So what did you notice as you looked at these? Pause and think about that for a second. We used inverse operations to solve the equations. If I had 3 times m, then I would divide by 3. If I had n divided by 5, then I multiplied times 5. So I started with division, went to the inverse of multiplying. Started with multiplying, went to the inverse, which was division. So we use those relationships between the operations to get back to the identities. So here we are at the end of the lesson. Hopefully you are feeling confident that you can solve one-step multiplication and division equations by relating an equation to a diagram, specifically a tape diagram. Hopefully you are feeling confident that you can use substitution to double check. You're going to get a solution and you're going to use substitution to say, is it the right one? All right, looking at the learning targets, we used substitution all the way through the lesson today and we solved equations. We're not yet to real-world problems, but we'll get there. So that concludes Module 4, Lesson 27, working with multiplication and division equations. If you've got questions, make sure you talk to your teacher. Make sure that you complete your problem set and make sure that you complete your exit ticket.